This is part 2 of homework help for homework 4C for Calculus 1. This is the second problem in homework 4C, and this is a classic problem, and we'll draw some diagrams for it and show you how to work out the variables in a minute. But first, let's write down what's going on here and what the problem really is. I've written this problem in terms of energy expended. So the idea would be that you would want to minimize your energy. Find a marker here. That's a decent color. Okay, here we go. So we want to know the energy expended overall because we want to minimize our energy. In the previous one, we want to maximize the strength of the beam or the stiffness of the beam. Here we're going to minimize our energy. All right. So it's going to be the same idea. You have to write an equation. Write it in terms of one variable. You want to find the value of that variable that makes the first derivative 0. So we're looking at energy. We want to send that first derivative to 0. That will be our critical point. It could be a max or it could be a min. Then the next step would be to find the second derivative, evaluate it at the value of the variable that sent that first derivative to 0. However, and that would tell you whether it's max or min. However, for this problem, I have spared you this step. Just do the problem up to here. The reason for that is the setup is fairly extensive. In terms of energy, the problem looks like this. The total energy would be the energy I spent when I swam plus the energy I spent running. Correct? Okay, so we're going to write an equation for that to start. Instead of knowing the total energy that I spent swimming, the problem gives me the rate of energy, 320 kilocalories per hour. So to get kilocalories, I have to multiply by hours. In other words, I have to multiply by time. We call that, you could say distance equals velocity times time, right? Or time is distance over velocity. This will give me the time. The time I spent swimming will be the distance swimming divided by how fast I swim. The time spent running is the distance that I run divided by how fast I run. So using that, we can construct this equation here, which is our starting equation. Total energy, E, equals the time spent swimming, the little subscripts S, times the rate of energy expended while swimming. Time spent running times the rate of energy expenditure while running. Now we have several variables here. We've got the distance swimming, the distance running. These velocities are specified. You run 1.5 miles an hour. No. You swim 1.5 miles an hour and you run kind of like a, I don't know, gazelle while they're walking. So don't worry about the numbers so much. The units are correct. Part of the reason for choosing these numbers is to make the arithmetic easy. Okay, but the setup is what we're concentrating on. So here's our basic equation, and this is the energy, and we want to minimize this energy. Right now it's a function of the distance that you swim and the distance that you run, and you'd like to have that changed. Everything else we have numbers for, but you want to change those variables into one variable. So the first thing we're going to do, which is what you should always do in problems like this, actually in any problem, is to draw a picture. So here's going to be my picture. This is the river. All right. And I know the width of the river. Okay. Let me find a different color here. The width of the river is 1.5 miles. Now, what else do I know? I know that I'm over here, so this is the person in the problem, and I know that down here is the boat that I'm trying to reach. Okay. I also know that the distance from here down to the boat is 6 miles. Okay. The idea is that you're going to swim either straight across a river or at an angle. So let's just draw the angle in because that's what we're, all right. And that line that I drew right there is the distance of swimming. From this point down to the boat is the distance running. Okay, the distance running equals, I'll call this y, for it'll seem obvious in a minute why I call that y, equals 6 minus y. So this is the distance that you eliminate from the running because you swim at an angle. Okay, so I'm going to change this all. So here are my two variables that I had before in the equation, and I want to change those into a single variable, and I'm going to use the theta here. And you'll see something similar in the book. If you look in this chapter, they didn't use energy though, but you get the idea from this picture. Now I've got one angle, and I'll write those trig functions again. Right. What's the cosine of theta? It's going to be, look at ds is the hypotenuse, right? It's going to be 1.5 over ds, because that's a hypotenuse. So ds equals 1.5 divided by the cosine of theta. Previously I said don't divide by theta. Well, you don't divide by theta to find the solution, but in writing this you can write it that way, but you would specify certain thetas are not going to work. For example, if you decide to swim at an angle of 2 pi, which would send cosine theta equal to 0, you would be swimming straight down right next to this bank and never getting on the other side. So of course you'd have to swim an infinite distance, I guess, all the way around the world and hope you come back by the boat. Okay, so now moving right along, let's write the sine of theta. Sine theta is going to be y over the distance that you swim, right? Opposite over hypotenuse. So now y equals the distance you swim times the sine of theta. Well, but I know what that is, so I can substitute it. That becomes 1.5 over cosine theta times sine theta. So y equals 1.5 times the tangent of theta. All right. And now the distance that I run is 6 minus y, which is 6 minus 1.5 times the tangent of theta. And in the typed equation here, you can see what happened. Here was my original equation, and it contained these variables that I needed to eliminate: distance swimming, distance running. For the distance swimming, I substitute this right here. So you see the 1.5 over the cosine theta. The 1.5 here is the velocity that you swim, and you can see I chose it so you could cancel it. All right, and now the distance running is 6 minus 1.5 tangent theta. You see that here. Here was a result of the substitution. You divide by 8 because in this problem you run at 8 miles an hour. Okay, and then the 320 and the 640 were from the original problem. There were numbers for those. So the number for ds was 1.5. The number for es, the rate of swimming energy, was 320. er 640, and the speed at which you run is 8. Okay, so everything's accounted for. Do some arithmetic, and you get E equals 320 over cosine theta plus 480 minus 120 tangent theta. You have energy in terms of the angle here. As this angle changes, the whole problem changes. The whole problem hinges on that angle. Now to find the critical point, we take the first derivative. So the derivative with respect to E, again, remember I have identified here what I'm doing. It's how E changes with theta. So that will be the derivative of 320 over cosine theta plus 480 minus 120 tangent theta. This is the expression that we have from the previous slide. So I'm going to carry out that derivative, and you can do that on the side, or you can, and it's pretty obvious. At any rate, the 320 is a constant, so it just comes down here. 1 over, so you're taking the derivative with respect to theta of 1 over cosine theta. You can do that as the quotient rule, or what I prefer is to write it like this: cosine theta to the minus 1, right? You could write, all right, And now I'm going to use the chain rule. The minus 1 comes out in front. I'll write it like that. Cosine theta, minus 1 is minus 2. And then I have the derivative of the cosine theta, which is minus sine theta. That's the inside function, remember? So negative signs are gone, and I get cosine squared theta times sine theta for the first term. That's what this is. Now, the derivative of 480. 480 is a constant, so its derivative is 0, and it doesn't even appear here, although you could write plus 0 if you want. Now I'm going to take the derivative of 120 tangent theta. The 120 is a constant, sits out in front. Derivative of tangent theta is secant squared theta. Right? Now I can do a little bit of algebra with this. Notice that secant, or remember that secant theta is 1 over cosine theta. So I have 1 over cosine squared theta is secant squared theta, so this term is really secant squared theta. I factor out the secant squared theta, and I'm left with 320 sine theta minus 120 times the secant squared of theta, and I want that to be 0 for the critical point. Solution of this is fairly easy. Okay, as before, secant squared theta equals 0. Secant is never 0, so there's no solution here. Forget about that. So then look at what's in parentheses, and that's very easy. You don't even have to use a trig identity for that. Right? Just use algebra. Sine theta equals whatever, 120 over 320, and then take the arc sine, and you get a value for theta. And that's all you have to do on that. Once you have it, you can go back and figure out the distance that you swim, assuming this is a minimum, which would be 1.5 over the cosine of the theta that you find from this equation, and the distance that you run, which is 6, minus 1.5 times the tangent of theta, and that'll be the distance swimming and the distance running. The third problem is that problem that you've seen before, and that is trying to figure out how much to order and balance out the cost of placing the order, the cost of storing an inventory. And here it looks something like this, if you remember what that function looked like if you look in the previous homework. And there was a minimum along here, and you're going to look for that. And in this case, you're going to do both derivatives and find the critical point and then find the minimum. Find out if it's a minimum by looking at the second derivative. For this problem, you don't have to derive the equation. It's given to you, and this is it right here. The reason, what you do have to do in this equation is sort out in your mind what is considered a constant and what is considered a variable. Now if all you're looking at, and that's what this problem is about, you're looking at Q, which is the size of the order. You want to decide how big of an order to place given these others. You could look at the whole problem in terms of all kinds of things. The cost of holding, there's other things to look at. So remember, if I'm taking the derivative with respect to Q, then let me clear that and okay. There's a Q here, and there's one up here. Everything else is a constant. This thing could just as easily have been written like that. The C naught and the N is just a constant. Might as well be the number 12. These terms, they're letters, but they're held constant. Could just as well be 4. And the CH over 2 could just as well be 6. Right. If you need to think of the problem like that, think of it like that. Those other variables, those other letters are constant for the purpose of this problem. Because I'm taking the derivative with respect to Q, everything else is held constant while I do that. This is also important for future work, as in Calculus 3, which is multivariable calculus. When I'm taking the derivative with respect to x, then all the y terms are considered constants. Right. if you can get that idea, then it's no problem. I'll take the derivative of the first term here, and to do that I have to use the quotient rule, or however you want to do it. I take the derivative of the second term, but that's a constant, so it's going to be 0. And for the next term, that's the derivative of 6q would just be q, so the derivative of ch over 2q respect to q is just going to be ch over 2. So here's my ch over 2. You don't see this term because it's 0, and this term is a result of the quotient rule. You want to set that to 0 and solve for q. And this is your answer right here. Okay. Now you can go ahead from this. I'm going to clear the screen a minute. Okay. Now this is your minimum right here. Right. You need the second derivative to find, or that's your critical point. That's the q for the critical point. Right now, you do not know if it's a maximum or a minimum, so you have to look at the second derivative. Let's take the second derivative. So if I'm taking the second derivative, means I'm taking the derivative of negative c naught n over q squared plus ch over 2. And we have the same issue. How many q's are in this equation? There's only one. This one right down here. This last term is just a constant. Its derivative is going to be 0. So I'd rather do it like this. Negative c naught n q to the minus 2 plus ch, sorry, where's that room there? Okay, when I'm taking the derivative of this, the minus 2 comes in front, multiplies the minus 1, it's positive. So c0n stay because those are constants. Then I subtract 1 using the power rule. The derivative of the last term is 0 because it's just all constant, and there's my answer. Now look at this. C naught is positive, n is positive, q is positive. This is always positive. You don't have to evaluate it. It's always going to be positive just by inspection. Because it's always positive, it's going to be positive at the critical point. Therefore, that critical point is a minimum.